Okay, good morning. Today we'll look at 3 examples for chapter 4, solved examples. And as I stated when I was covering the theory behind this transient analysis, we have the standard equation. We will use this equation. There are 3 quantities in each equation. One is the starting or the initial values, then the final value, right? We need a start point and an end point during the energy transfer phase, and then how long it takes for that energy to be transferred. The 3 quantities, and our job as an engineer would be to determine those 3 quantities. So let's look at example 1. Okay, in example 1, problem statement is that the switch in the circuit has been closed for a long time before it is opened at t equals 0. Then question is being asked, find the inductor current as a function of time for all values of time t greater than or equal to 0, meaning after the switch is open, right? So we are not required to find any equations before the switch was opened. Key distinction. All right, so the first thing we want to do is we want to determine the circuit condition at t equal to 0 or just before t equal to 0, meaning we need to look into the past to find the initial value of the current after the switch is flipped. So before time t equal to 0, the switch was closed, so the circuit would look like this. We have an inductor and then a few resistors on the right. Okay. Now, switch is closed, and the key word here is that it was closed for a very long time. For a long time. What does long time indicate? Yes. So long time indicates that the system has been at steady state for a long time, or sufficient time has elapsed in the past so that the inductor has reached full charge. When the inductor has reached full charge, it behaves like a short circuit. So in the past, if inductor is behaving like a short circuit, all of the current flows through the inductor. The circuit simply reduces to the current source and the inductor that behaves like a short circuit. So as soon as you read the words long time, should equivalent is that it has reached steady state. So if the inductor is behaving like a short circuit, all of the current is flowing through that inductor. 2 Henry inductor and IL coming down. Now, all right, I'll wait until let's take a pause. Let me know if you have any questions. Yes. It's just 2 Henry. 2 Henry inductor. It's the value of the inductor. So again, we are not concerned with the past, meaning before the switch was flipped open, we do not care, except we need the value to establish the initial value for our analysis. Make sense? Right? So all the current is flowing through there. Now, for time t equal to or greater than 0, the circuit flips open. The source is disconnected. The only thing that's left in the circuit are basically the inductor and the 3 resistors on the right. So the circuit is now changed. Okay, we are drawing two different circuit diagrams before and after the switch is flipped. Okay, two different circuits. The reference direction for IL is given to us. We stick with that same direction. We don't change it. 2 ohms, 10 ohms, and 40 ohms. Now, does the circuit have a source connected anywhere? So what kind of a response is it? It's discharging, right? It has stored energy. Stored energy is being discharged to the 3 resistors. So if it is a discharging or natural response problem, what is the final value? Always. In this case, we're trying to find IL. So IF, we can say, we conclude natural response. And so IF, final value of the current, has to go to 0. IF is 0. Then we want to find the starting point of our analysis. For the starting point, we look into the past, right? Current through an inductor cannot change instantaneously, meaning right at the beginning of our analysis, the current through the inductor is still the current that was flowing through the inductor before the switch was flipped, which is the value of the current source, 20 amps. So II, I'll write this down here. Current through inductor cannot change instantaneously. Therefore, I or I0 is 20 amps. And then we find, so we have the starting point, we have the end point. All we need to do is to find the amount of time it will require for it to discharge, which is tau. Tau, time constant, is L over R. Which R do we take? The one in series, the one in parallel? It's discharging through all 3 resistors, so it has to be Req, the total equivalent resistance as seen by the inductor. So we have to remove the inductor from the circuit, find Req. The reason we have to find Req again is because the inductor has stored energy. All 3 resistors are connected to that inductor. So all of that energy is going to discharge through all 3 resistors. And so we have to find Req. In this case, it's 2, 10, and 40. So Req is 10 in parallel with 40, and then in series with 2, which gives us, let's see, 400 divided by 50 plus 2 is equal to 10 ohms. And my tau is L over Req, 2 over 10, 0.2 seconds. 0.2 seconds. This is how we determine all three values. Once you have all three, you simply take your standard expression and you plug in all the three values and you reduce it as much as possible, and that is your final answer. Okay. X of t, in this case, x is equal to I, and so the equation would be IL of t is IF plus I0 minus IF into e raised to minus t over tau. IF is 0, so I have 0 plus 20 minus 0 into e raised to minus t over 0.2. And that is my final answer. 20 into e raised to minus 5t. This equation is valid for all values of t, meaning all values of time greater than equal to or greater than 0. If you plug in time t equal to 0, what do you get? 20 into e raised to 0, 20 times 1, 20, which is the value of the current at t equal to 0, 20 amps. And then from that point on, it's an exponential decay, right? So you plug in t is equal to 40 milliseconds, you find a value, and so on and so forth. And again, going back to that point I made, after 5 time constants, it will lose more than 99% of the stored energy. Okay, the value of the current remaining in the inductor will be very, very small. Mathematically, again, we can plug in t is equal to 500 seconds or 1000 seconds or 1 million seconds. You would expect to obtain a mathematical value for the current. But after a certain point in time, we say it reaches 0. Yes. I0. So this is I0. I0 or II basically represents the starting point, meaning the value of the current or the quantity at time t equal to 0, or I stands for initial, the initial starting point. All right, questions? Other questions? So I'll summarize again the step-by-step process. We have the standard generic equation that can be applied for both natural as well as step response. We need 3 quantities. We need the starting point, we need the end point, and we need the time it takes to do that energy transfer, whether it's natural or whether it's forced, or step response. You take a look at the circuit conditions before and after the switch is flipped, draw out the circuit, determine whether you're analyzing for step response or natural response. In this case, it was natural, and so final value is always 0. All right, questions before I move on to the next. Okay. Then let's look at example number 2. Similar example. Says the switch in the circuit has been in position X for a long time. Instantly mean it's steady state. That steady state could be completely discharged or it could be fully charged. So let's draw out the circuit when it was at position X. So for time t less than 0, we have a capacitor that is connected to a voltage source for a long time. And that means the capacitor has reached full charge. So this is 100 volts. The capacitor has reached full charge. For time t greater than 0, switch flips to the right. The only thing remaining in the circuit, similar to the previous one, is the capacitor and 3 resistors. Very similar to the previous one. Yes. The resistor on top, which one? 32K? No, the 10K was here while it was charging on the left side. So in position X. Yeah. So once the switch flips, the left side gets disconnected. And because it gets disconnected, so earlier when it's at position X, capacitor is connected to the left side of the circuit. The right side is not connected. And then at time t equal to 0, the switch flips to the right. The switch disconnects from the left and connects to the right side of the circuit. And the left side is disconnected. Mm-hmm. Yes. Oh, you mean voltage drop across that resistor? It won't. So the question being asked is, would there be a voltage drop across that resistor? The answer is no. The answer, the explanation for that is when it first begins charging. When it first begins charging, yes, that resistor will have a certain amount of voltage drop. And so the voltage across the capacitor will build up slowly. Once the capacitor reaches full charge, it behaves like a open circuit. It's behaving like an open circuit. No more electrons are flowing through. There is no more current flowing through the circuit. If there's no current flowing through the circuit, the voltage drop across the resistor would be 0. So when the capacitor is fully charged, the voltage across that resistor will be completely 0. And the fully charged capacitor will have a value of 100 volts. So if you were analyzing for time t less than 0, then we could derive an equation for a charging response. You would simply have initial value, perhaps assume as 0. Final value would always still be 100 volts. So it wouldn't matter if you have multiple resistors connected in series. So good question. Okay, so now similar to the other one, we know our initial value V0 is equal to the fully charged capacitor, which is 100 volts. We'll find Req as seen by capacitor. Req is 60K in parallel with 20K, which is then in series with 32. And that gives me 80K, 80 kilo ohms. Tau is simply the product of R and C. In this case, it is Req times C. And so 80 kilo ohms. Actually, let's do it this way. 80,000 times my capacitor value is 0.5 microfarads. So one time constant is 4 milliseconds. 4 milliseconds. And I would also add this here that my initial value for V0 is 100 volts and Vf, because it's a natural response, would be 0 volts. Does that make sense to everyone? Right, after, yes. Yes, right after it flips. Because similar to the inductor, the voltage across a capacitor cannot change instantaneously. And so if the voltage cannot change instantaneously, that means that right after the switch is flipped, when it's disconnected from the source, the capacitor still holds 100 volts of charge. And that's where we get the initial starting voltage. All right, any other questions? Yes. Yeah, capacitor acts like open circuit, but yeah, but after T is equal to 0, when the switch is flipped, we are no longer concerned with that resistor. Anything that's on the left side of the circuit is disconnected. So it doesn't matter what resistors are connected. There could be 100 resistors and we wouldn't care. Yeah. All right. Does that make sense? Yes. Let's see, 80,000, 80K, 0.5, 10 raised to minus 3 gets rid of 1,000 over there. So you got 80 into 10 raised to minus 3. And 0.5, 0.5 goes 8, 4, wait. Yeah, 40 milliseconds. Thank you. 40 milliseconds, 40. So then the expression over Vc of t can be written as Vf plus V0 minus Vf into e raised to minus t over tau. Plug in all three values. Final, of course, is 0. 100 minus 0, e raised to minus t over 40 milliseconds, 0.04. Reduce it, and you obtain 100 into e raised to minus 25t volts. This equation is valid for all values of time greater than or equal to 0. Right, let's pause. So here makes sense? Similar? Any questions before I move on to the third one? Okay. Derive an expression for Vc of t is greater than time t greater than 0. Nothing else is given to us. Doesn't state it's been there for a long time, doesn't say anything. So let's look at the circuit. Okay, as usual, we'll draw out. Let's draw out the circuit for time t less than 0. What do we see? If we look at the circuit, it says at t equal to 0, the switch is going to be flipped open, which means prior to t equal to 0, the switch was closed. So again, there's nothing given to us. It is your job as an engineer to read the problem statement, look at the system, and understand what it's telling you. So in this case, the switch is closed. If the switch is closed, the current source is passing everything through that short circuit. Now, obviously, in real life, we would never do this. We would never take the output terminals of a source and short it out. Okay, this is simply a schematic representation of a system. Just to illustrate that before the switch was flipped open, everything was connected internally to the source, meaning the source was not sending any energy to that capacitor. Okay, the right side of the circuit essentially is not connected to the circuit because it's in parallel to that short circuit. Okay. Second thing is, nothing else is stated about the initial condition of that system. Right? Nothing else is given to us. So if nothing is given to you, and we see that the source is not connected to that capacitor, we simply assume that the initial energy in the capacitor is 0. Okay. If it's not given, right, explicitly not stated that there is any charge in there, whether it was connected or not, then you simply assume that the initial starting energy is 0. So since it is disconnected and because nothing else is stated, assume V0 is equal to 0 volts. Now, t equal to 0, the switch is flipped open. So for time t equal to or greater than 0, the circuit looks like this. We have a source. Source is connected to a single resistor and a single capacitor. What kind of a response is this? Natural or step? If there is no source, then it's a natural response. If there is a source connected, it's a step response. Initial value is 0. Final value can be determined by applying Ohm's law. So final value of voltage can be found by applying Ohm's law. 10 milliamps times 2 kilo ohms. (2000) 10⁻³ to 20 volts. And tau is simply RC. So milliseconds. You have your initial values, your final values, and your time constant. Simply plug those into the equation. So Vc of t is Vf plus V0 minus Vf into e raised to minus t over tau. E raised to minus 50 t volts for t greater than or equal to 0. Yes. That is before time t equal to 0. Okay, so the question being asked is about time t equal to 0. For our analysis, we don't really care. So if you look at this, you're simply asked to find Vc of t for t greater than 0. So oh, because it's a short. So the question being asked is about the short circuit. If you have a short circuit in in any electric circuit, anything that's in parallel with the short circuit is effectively removed, because all the current or all the everything would just go through that short circuit. Everything else is kind of redundant. Okay. All right, so we'll end class here today and we'll get to the fun stuff beginning on Wednesday, which is chapter 5, AC analysis. Yes. 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 Students haven't begun the homework? All right, I'll think about it. And so the question being asked is about the homework due date. And so, all right, I'll think about it and maybe I might extend it if students want it. All right, I'll ask students in the next 2 classes and see what the response is.